There have been some remarks about the weather here. I have to say, Jorge, I love this weather. It makes me feel at home. So, the next speaker, Professor Xiaogang Liu from the National University of Singapore. Professor Xiaogang Liu is highly recognized in the field. He makes magic with nanocrystals. He combines chemistry with physics and biomedical applications. He designs wonderful nanocrystal structures, does the physics to understand what's going on, and then where we often end, and we say at the end of our article, it's very promising for this and it's very promising for that, Xiaogang Liu makes those promises come true. He really translates what he finds into real biomedical applications that are useful for the world. He won many awards. I will not mention them all, but earlier this year he was elected into the National Academy of Science in Singapore, and we are in the same WeChat group with, I think, 150 Chinese researchers, and my phone wouldn't stop buzzing with all the people congratulating him. He's really well liked and respected in our field. It's also very appropriate that he speaks here at the SHIFT conference. If you go to his website, he has a mission statement, and he says, "Our research vision is to shift the chemistry of fluorophores from trial and error to molecular engineering to gain tailored properties to suit applications." So I'm looking forward to a wonderful and inspirational talk by Professor Xiaogang Liu, where he will, I'm sure, show wonderful nanostructures and how they are applied in real-life applications. Professor Liu, let's welcome Professor Xiaogang Liu.
Thank you, Andre. First of all, I want to thank the organizer, especially Jorge, for your very kind invitation. I really enjoyed my trip here, although it's my second time, but I feel like this time it's actually, I wouldn't say it's better than the first one, but it's more special for me, because this time also I came along with my students. I really enjoyed the network discussion, poster sessions, with all the students. So over the past few years, we have heard a lot of wonderful talks on nanoparticles, especially luminescent materials. So when you look the theme of this conference as a spectral shaping. So spectral shaping, we already heard a lot of luminescent tuning modulations. So I think my talk, so I saw maybe I talk a little bit different. So I focus on the second part of the theme of this conference for biomedical and energy applications. So I focus on energy applications, especially biomedical, some of the biomedical applications. First of all, I would like, I think first and foremost, I want to thank my group members, current and the past, for their contributions to my research. Also, I want to thank, I think I'm not sure if I have laser point somewhere. So I also want to thank my collaborators around the world. Some of the collaborators actually sitting in here. They're also tremendous scientists. Yeah, also want to thank my collaborators. So many of my collaborators, they're tremendous scientists on their own. They have helped us to really push the scientific problems, help us really solve the big problems in many fields of research. Also, I would like to thank the funding agencies from the National Research Foundation, Singapore, A-STAR, Ministry of Education of Singapore. Okay, but the laser is not. Oh, okay, now I have the laser. So, over the past few days, we heard a lot of this interest in different type of materials, luminescent materials for bioimaging. So here, I highlight some of the most commonly used luminescent materials for imaging. Organic dyes, metal clusters, quantum dots. We heard of Louis, the beautiful talk on plasmonic nanoparticles. Also, we heard a lot of this rare earth dope nanocrystals, up conversions, nanothermometries, super resolution imaging. So that's good. So I feel like I will not talk about rare earth based nanocrystals, because I want to focus on the problems in this field, especially for how to improve the resolution, improve the imaging contrast, how to solve the real problems. So if you think about different biomarkers, so for chemists, I'm a chemist, we have learned how to modify, synthesize the particles with a different size, shape, morphology. We can actually coat the nanoparticles on the surface with different types of biological species. So we actually can select a target cancer cell. So we have solved a lot of problems, but there's still the challenges ahead. So the challenge is how we combine these nanoparticles with biological systems or device for real practical challenges. For example, how we can integrate these nanoparticles with some of the imaging technology we currently have. For example, the MRI imaging systems, PET, spectral, X-ray imaging systems. Another most important challenge, I think, for bioimaging is how we balance the tissue penetration and the resolution. So I think we have demonstrated many these bright nanoparticles. So for imaging, we want a very bright emission nanoparticles. But most of the demonstration is actually based on the cell levels. So if you want to go to cell level to animal, in vivo models, so the major problems I would think is the penetration, means the excitation source, and also the emission of the nanomaterials we use. So there's a two-way traffic. Not only we want to have the excitation light penetrate through the tissue, but also we have to think about how we let the emission from the particles penetrate through the skin or the tissue, then can be detected by the photodetectors. So this is two-way challenge. Not only the particles we can have emission penetrate through the tissue, but also how we can, so we have the near excitation source. So we solve the first problem, right? The excitation, near-infrared light can penetrate through the tissue. But also, we have to think about the particles, how this emission can come out of the tissue. So if you look at the solar spectrum, we have achieved so far so many different examples, excitation on the near-infrared light. We heard a lot of talks using upconversion nanoparticles because of the benefit of using near-infrared light as excitation. We actually can push the excitation to the second optic window, near-infrared light spectrums. But that's still not enough for biological imaging, for in vivo imaging. So we can talk about near-infrared light, the penetration, compared to visible light. It's already much better. As you can, but maximum, I would think is 1 centimeters for near-infrared light. But for visible light, it's less than 2 millimeters. So the challenge is how we can go even deeper. So maybe we can think about X-rays, gamma rays. Those are the available technology. So because the X-ray, the whole body imaging, the penetration. So the challenge, of course, for bioimaging, you need to find the right materials. So what type of materials we can use? Obviously, we can learn from the past. Old days, people using scintillators. Those scintillators can convert high energy beam excitation into visible light. So this we call the scintillators, X-ray scintillators. So of course, in the past, these scintillators, actually we have been using these scintillators till now. So for biomedical imaging, still using the conventional Ball crystals. So those Ball crystals have limitations in terms of chemical synthesis. Typically, the temperature required for this synthesis it's actually close to 800 degrees C. You need a thermal treatment. Obviously, this bulk crystal is not suitable for biological labeling, right? So first thing we want biological labeling is small particles, biocompatible surface. So this is a challenge. You think about the future imaging technology should be flexible, conformal. It means not only we can make particles inject to the tumor site, but it's possible to make a flexible X-ray imager. So that's for 3D for imaging of a 3D object. So if you have a flexible X-ray imager, that would be much better. So for example, if you want imaging, this is my risk. So conventional strategy, just put the flat panel. So I place my hand onto the flexible panel, but it doesn't give me 3D profiles. But if you have a 3D X-ray imager, I can wrap around my wrist, and then you can take a 3D image of the structure. So this is the future challenges. So we have been thinking, try to find the right materials for X-ray scintillations, for X-ray imaging. So a few years ago, my postdoc, Qiu Shui, now a professor in Fuzhou University in China, so he realized this very interesting optical phenomena, perovskite nanocrystals. Because around the year of 2016-17, the perovskite nanocrystal is a huge push for photovoltaic solar cell applications because of the high absorption efficiency. But of course, for perovskite nanocrystal, the problem is the photostability. So thermal stability. But we actually realized as a postdoc, my postdoc, Qiu Shui, realized maybe this crystal is good for scintillations. So he actually did test these nanocrystals on the low dose X-ray irradiations. He actually can get the tunable radioluminescence from these nanocrystals. So this is quite remarkable. We actually can make a multicolor radioluminescence. But of course, we still have problems with the application where we need the multicolors. This is unlike bioimaging, we need the multicolor labels. But for X-ray imaging, seems we don't need a multicolor. So we still have puzzled with this demonstration. But anyway, so this nanocrystals are excellent X-ray scintillators. So if you can compare to, not as good as the conventional, the most popular scintillators, cesium, iodide, thallium. But it's right there. So it's very close. But also, it's nanocrystals. We can actually convert these nanocrystals. We actually can print this nanocrystal on to photodiodes. This is actually showing. This is a conventional standard X-ray imaging panels. So this costs about I was saying about 30,000 euros. It's quite expensive. So the main configuration you can have this. The packaging is aluminum foil. The underneath is the scintillators. So in conventional panel, imaging panel, so this is cesium iodide bulk crystals. So actually most of the scintillators is actually made by Hamamatsu from Japan. So they actually dominate the market. And then underneath the scintillator is the photodiode, the silicon detectors, and they have the TFT sensor. So this is the basic component of the X-ray imager. So we actually replaced the bulk crystals with our perovskite nanocrystals. So actually we can achieve very high imaging of this is animal structures. We can also get a pretty high the MTF functions. So this shows the resolution. So we actually can, using this nanocrystal, get about 100 micron meter resolutions. So a few years ago. Okay, so of course this is wonderful materials for imaging applications. But the problems, two fundamental problems with these perovskite nanocrystals. The first problem is actually the photon scattering and the self-absorption, especially from this perovskite nanocrystals. So you think about, if you want to improve the light harvesting, the X-ray photons harvesting, right? Normally you need to increase the thickness of the scintillator layers. But if you increase the thickness, so it means the photon scatterings, also perovskite self-absorb the emissions. So that's a major problem, because you want to have a transparent layers, but at the same time you want to improve the absorption. So it seems quite a challenging issue. If you want to absorb more X-ray photons, then you need thicker layers. But the thicker layers have the problem with photon scattering, and also the self-absorption, and also make the scintillators non-transparent. So that's the trade-off. The other thing is the photo thermostability, right? Perovskite nanocrystals are wonderful materials for solar cell applications, LED applications. So every month you can see the community, for solar cell LED community, they beat a record almost every month. Now I don't remember the record. So for LED, maybe 33% conversion efficiency. Of course, the problem is most of reported device cannot last for 1 hour. The problem is the heating, the overheating issues. This nanocrystal change the phase, change the size, so the optical property change. So that's of course, there's many engineering solutions, but still, photo thermostability is a big issue here. How we do this, how we solve these problems? So actually engineering comes in. So I have two wonderful postdocs. Actually, he come with an engineering background. They thought about why not using optics, fiber optics, because we know fiber optics are excellent tools for light harvesting. For light, you can control the light. You can do lasing. You can control the light to propagate through the fibers. So we had this kind of new design. So we want to have. So why not we can have a thicker scintillator layer, but we can embed this microfiber optical array inside the scintillators. So basic designs. So we want to have this double tape. So double taped this optical fibers. So why we want this double tape? So based on simulations, we actually can harvest all these scattered photons through the core shell layers. So the reflect index design is very important. So we want to have the matrix, of course, is the perovskite. In this case, perovskite scintillators. The reflect index has to be larger through the shell here, the cladding here. The inside the core also have the larger reflect index than the core here. So in that sense, the scattered photons can enter into the fibers, then through the total internal reflections, then actually you can reach the photodetectors. So this is a basic design, actually a very powerful design. I never saw because based on our simulation. So this shows not only for X-ray, we actually can increase the efficiencies without fiber, with fiber, or without fiber, just scintillator only. You can see the enormous enhancement with the fiber optical arrays. So this is especially useful for gamma ray because the gamma ray penetration much more powerful than X-ray. So we want a very thick scintillator layers. So this actually solves the problem. Let's give you some the real results. So this shows the optical fiber arrays. You can see this actually 3D printed microfiber arrays. So we actually can, of course, all this is double tape. So double tape the optical fiber designs. So the opening is about 5 micrometers. So we can print thousands, even millions of these small fibers over large areas. Then we can actually embed this perovskite scintillators inside. So we can embed this fiber array inside the scintillator layers. So this basic, very simple imaging design. So this shows the scintillators covered onto the microfiber arrays. There's a device imaging, very simple. You can use a digital camera, take the imaging. So it shows the internal structures. So now the resolution is about 25 micrometers. So this is already, I think it's already state of art. You can see very high resolutions, very simple designs. But actually without this microfiber arrays, we actually don't see any of these fine features. Okay, so let me show you the gamma ray. So this is the most challenge. So a lot of scintillators are good for X-ray, even gamma ray detection, but not the imaging. The imaging is pixelated. You have to have a large area. So that's actually the most challenging issues. So with this design, we actually can achieve this, the gamma ray not only detection, but also imaging. So you can see the different NH 10 mega electron volts and 6 or 10 mega electron volts, they actually shape change a little bit. So the technician at the radiotherapy facility in Singapore is from a National Cancer Center because they are using the gamma ray for radiotherapy, treat the tumors. For small localized tumors, now the gamma ray is actually an advanced image therapeutic technology. So without this fiber, you can clearly see there's no signal at all. So I just want to show you because seeing is believing. Okay, so this is the medical facility. Very big, very expensive setup. So we actually place a piece of the scintillator with the fibers. On the left, you can clearly see. So for the technician, they actually can use this tool to quantify the gamma ray, the energy source. On the right is without fiber. Don't see anything. So this is a very convenient to allow us to visualize the gamma ray X-ray source. We can do the imaging. So the second problem I just mentioned for X-ray imaging using perovskite is the photothermal stability. Right? We show this material is good for X-ray imaging, but for biological labeling, perovskite nanocrystals cannot do that. So this is, we have been thinking about this very, very hard. We want to have a very stable, upconversion nanocrystals. We have been working on for the past 16 years, but we never realized that this upconversion, real doped nanoparticles, they're actually excellent nanoscintillators. In the past, we just never tried to excite these nanoparticles with X-rays. So once we realize that, so this is quite interesting. Not only these those real Earth-doped nanoparticles, core shell nanoparticles, give a radioluminescence, they actually give this a position luminescence. So we're thinking maybe we can use this position luminescence to do the flexible X-ray imaging. So we come up with this concept, X-ray luminescence extension imaging. So we mix this nanoparticle inside flexible, for example, PDMS. So we can wrap around the PDMS, so we can place it into the 3D electronics device. And then we can take out of this the imager with the scintillator. And then we hit this. Sometimes we don't need a hit. Because of precision luminescence, no actually can achieve the imaging after we switch off the X-rays. So that's the benefit of having position luminescence. So we can shut off the X-ray excitation, then we can take the imaging. So this is much safer. So with this flexible substrate, we can stretch to improve the resolution. So 500 times stretching. So we actually can improve the resolution down to the 20 line pair per millimeters. So this equivalent around 20 micrometers resolutions. Yeah, so I showed the conventional X-ray detector, these imagers, but you cannot resolve the 3D structure of this electronics. So the imaging is overlapping. But with this flexible substrate, actually you can roll off, you can reconstruct the 3D structures. Okay, so I talk about this X-ray nanoparticle scintillators. So we are thinking for biomedical, this symposium or conference all about biomedical applications. So this really challenges, people want to look at the cells, do the biology imaging. People want to do in vivo imaging. We also think about, how we can translate this nanoscintillator into in vivo dosimeter. So this is a really challenging issue. So you think about, so we have been talking to X-ray radio technicians. They actually feel like this in vivo dosimeter very important because for cancer patient undergoing the radiotherapy, how much of the dose absorbed by the organs specifically, how to quantify is that very, very challenging. So they only know the dose rate coming from the machine, right? The machine has some reading, but the machine can go wrong. You really don't know how much, for example, liver, for example, in the GI tract, how much dose localized in that region. So that's prompted us to think about, can we develop this in vivo dosimeters? So those in vivo dosimeters has been reported. So I've shown this one of the examples. So this is semiconductor-based X-ray dosimeters. But of course, you look at the dimension, it's relatively big. So it's almost 2 centimeters long. So this is still challenging. You think about, you swallow this, but also this does not give you this reading of the local temperature and the pH. So we had a lot of talks on pH sensing, temperature sensing. So we're thinking, can we make an ultra small capsular dosimeters that can simultaneously monitor the dose rate, the local temperature, and the micro environment, pH. So that's our goal here. So we did it. So we have an excellent postdocs who come up with this interesting capsule dosimeter design. I just want to quickly show you. This is the next slide. I'll show you the configurations. But the basic designs come with this precision luminescence materials. I just showed you the nanoparticles is the key component to detect the dose rate. For the pH sensing, we have this wonderful polymers. So we combine inorganic, organic materials. This is the pH sensing polymer materials. So from the pH sensing, because of this polymer change the colors, from the colors, we actually can, color change, we can detect the pH. So this is the assembly of the individual components. So it's 8 parts. If you look one by one, so antenna here, microcontroller, there's dose. This is a dose sensor here, the chip. So this is optical fiber embedded with the precision luminescent materials. This is fluid cavity. So this is a microfluid device. Take the fluid from the GI tract. So you have the fluid, can analyze the pH, also can analyze the temperature. We also have the battery. So the packaging is outside, is biocompatible polymers. So everything in one set. So very small, actually, very small. So actually, you can look at this much smaller than it's actually the standard capsule size 2, okay? So you can, over the counter, this the capsule, typically sold in the pharmaceutical industry. So this is on the X-ray excitation. You can see the radioluminescence. So we can couple using Bluetooth technology. So this actually shows the 3 channels, the X-ray reading, temperature, and also pH. I just want to show you what it looks like. Yeah, we have done some in vivo studies. Of course, it requires not a mouse. We need bigger animals, for example, rabbit, monkeys. Actually, my postdoc wanted to try it himself. But I said, no, we have to, with the proof. Yeah, he showed me. Yeah, but, it takes a few days, you pass out, yeah. But you can see we increase the radiation. You can see this is the 3 channel. Dose rate increase. The second is sorry, I apologize. We have a computer issue. The resolution not good. So now it's increased with the pH sensing. We add the basic solution. You can see. So the first channel is actually dose rate, no change at all. Now let's wait for a while. You can see the pH significant increase. The pH become a basic. Then interestingly, the temperature change a little bit. But we don't know it's because of the chemical reaction. But then they flat out. So the capability, dynamic monitoring, the dose rate, also the pH. We have pH resolutions at 0.1. You can see different pH, the stability over 4 hours. So this could be very useful for gastric acid monitoring. So a lot of, myself sometimes have the gastric problems, always acid reflux. So the medical doctor normally also, they have this kind of capsule. So the patient has swallowed for 3 days, 72 hours. So they can monitor the acid, the pH inside the GI tract, and then give you a prescription. So that's the technology. But of course, the current technology is the capsule size is actually very big, but also it has some limitations. So not only our capsule can use it for X-ray detections, but also the pH, so very sensitive pH sensors. Okay, so next few minutes I want to talk about this assistive technology, how we can translate luminescent materials for technology application that can really, we can feel that. People always talk about luminescence detection, photo detection, right? How we can use that for this specific technology called assistive technology. So assistive technology covers many areas. The main thing is how we can use this device to improve the living standard or for people with disabilities, improve their confidence, independent livings. So how, when we getting older, everyone's getting older. Eventually, we want to, we cannot even move the hands. We cannot sleep well. So how we can take advantage of the technology, improve the writing, hearing, right? And also speech recognitions. Just to give you 3 typical examples for assistive technology control the typing. So this image probably looks familiar because we know Stephen Hawking. Stephen Hawking's, he cannot really move. He has ALS symptom. Also, those patient, Parkinson's disease, cannot really type the computers. How should they, perform the typing? For example, the one way is voice recognition. So they speech, of course, and then the software then translate the voice into specific command to control the typing here. But the limitation, of course, you cannot perform the task in a very noisy environment. And also the software processing takes a lot of time. The other technology, eye tracking, okay? But of course, Stephen Hawking, he shared his experience. He said useful, but very tiring after a while because how you translate the command, you look at the right, you look at the left, look at the right, look at the up. So you have to constantly change the direction of the eye directions. So the very tiring experience, okay? The recent one seems the most promising one is the brain-computer interface. So Elon Musk showed a lot of examples, right? You use a brain-computer interface control the monkeys, the thinking to move around. But of course, this is relatively invasive. You have to implant the chips, at least underneath the skull. So then the question is, can we use luminescent materials? Light, rainbows. We see the rainbows over the past few days. I keep thinking, you're using colors. The colors can be wonderful, okay? But the question is how we can the colors into specific command to control the computers. Think about the mouse. Actually, never realized that the mouse, this dinosaur's toy, many of you, perhaps you played with your kids. So because of interesting facts about the bitings, the biting force is very strong, can up to 200 pounds. That's why when you fight with someone, you cannot beat him, you can bite him. The biting force, 200 pounds, huge amount of force. So that's thinking, maybe if you can come up with mechano-luminescent materials, maybe you can use a biting to control the color output. So the one color is one command. So that's we come up, why not think about some mechano-luminescent materials? So mechano-luminescence, as a chemist and material scientist, we can find it. It's out there. Zinc sulfide, copper sulfide, wonderful materials. We just never thought about using these materials to control this interactive mouse guard. So this is how we design. We actually want to embed this mechano-powered the luminescent materials inside the fibers. So this everything, this is the configuration. So you can see we have two arrays, the fiber arrays with 3 different colors. So these materials emit different colors on the compression, stretching. Just 3 colors, but different arrangement, 2 arrays. You form the combination theory, you can actually get this 21 different biting patterns. Different patterns, so fiber 1, fiber 2 give the different color output. So then you can combine these 2 color output. So we have photodetectors. Then through the machine learning, we heard a lot of machine learning. So that gives us the control. So this shows some of the biting patterns. So different individuals have a different biting habit. You know, biting left, biting right, biting front. You can also change the biting frequency. You can bite 2. Depending on the biting, the area covered, you can actually change you can send a specific command. So this shows the real device design here. So we have this mechano-luminescent materials. We have this flexible circuit, this RGB sensors. So convert these colors. The colors is a signal sent out. We have the mouse guard. This is a antenna here. So we are using Bluetooth technology. So this shows the mechano-luminescence arrays inside the fibers. I just want to show you so some of the characterizations. So you can compress this, stretch. It shows to give you different colors. Yeah, because stretch, this is not a very strong force. The biting is much stronger force, okay? But this is easy for proof of concept. You can see now we compress this, stretching this, give you a very nice different colors. So we can convert this color. This shows arrays. This shows a 4x4 arrays, but that gives you can do the math, gives a lot different the signal output. So for demonstration, we actually use just a 2x3 arrays. This shows compression. The biting so works the same ways. You can get different color output. Okay, so this is once we have this materials, now we want to demonstrate basic. So they call the Internet of Things. So keyboard typing. So we want to create a virtual keyboard. Okay, so for users convenience. So we want to create online. So it's a virtual keyboard. For example, like this. So if you want to type love, okay, for example, love here. How we type this? The first thing we have to use a mouse. We still use a mouse, but this is a virtual mouse. So by biting, you see the command, the number here, the 5, 1, 2. So this is each function. So the function 5 is when we bite, maybe by the left, we turn on the operation mode. So the alphabetic keyboard shows up on the screen. And then we bite another bite, maybe by the slightly left, 1 here. So the 1 is enter. Okay, so you can see we find that we move the online mouse to this keyboard. We stop right here. So this is the L. Then here, we enter, so we type L. And then O here, love, right? The O is pretty far away from here. So where's the O here? It's right here. It's up left. So we just, how we move that, we just by another position. 3 here, 3 is go up. So we move the mouse up, then slightly left, and then we enter here. The V here, slightly far away from here. So if you look at the V is right here. So we have to move a long distance. So here it shows we by the 5, actually 6. The 6 is moving to the left. 6, 6, because it's moving quite a long distance. So we have moving the cursor to the left, then lower the cursor, right? So it's the 8. 8 is lower down the cursor, then we enter. So this shows the mechanism. You might say very complicated. How the user can learn this? Actually takes a few days practice. Everyone in the audience, no problem. So it's we tested. So I was amazed that so after practice, anyone can actually perform the typing. Also the phone, you can think about. You can also use this button to control phone calls for emergency phone calls. I just want to show you. This is the typing here. So this is for Jorge. Okay. So it's kind of slow, but bear with me, patient. Okay, love, takes a while. S, edge. Okay, here's very important. Okay, the F is very important. Okay, because we don't want to miss the F word. we don't want to miss the F word because I asked my postdoc very careful. Without the F word, then it would be terrible. Yeah. Okay, so show something else. Yeah, think about for people, you have the mobility problems. Can we, move around the wheelchairs just using biting? That's a very simple function. So that shows it can, so we convert this electronic wheelchair. So now everything is controlled by biting here. So this shows the trajectory of the wheelchair movement. So we intentionally put this chair right here. You can get around this chair. So no problem. It's very convenient. Yeah. So he's finding his desk. So you can see it's very smooth. Actually, for wheelchair control, it's very easy. So of course, we want to, hopefully this kind of technology can benefit people who have special needs. Sorry, because I tried very hard. The staff is trying to help me with the sound system, but we cannot. But actually, Antonio here, you might like it. So of course, I want to play this song. I can tell you what song is this. The melody is "Happy Birthday." Okay, but of course, Antonio might say that's not the music. In Spain, we flamenco, much pace, much faster pace. So that we are not getting there. You can see that we can play slow music for flamenco. This kind of fast pace, we're working on that. So hopefully we can use a mouse guard control, not only play flamenco, but also maybe play games. So the online games very fast. So that of course requires a special design. Also the materials technology here. Okay, so we also tested, the precision, right? Engineering always care about how reliable this technology. So we actually tried this, the NUS, the field, So my student tested the wheelchair navigation over 1.6 kilometers. Just keep doing this. And from the GPS data, so we monitor the GPS data. You see it's quite reproducible. The control, the precision here. We can do the different pathways. So this shows this technology. Of course, this is the first generation, the mouse guard. eventually, we are thinking, can we have a better, now the challenge, of course, is the speed. User by, take some practice, but also the response time requires improvement. So I think I give you a taste of what we can do with luminescent materials, not only some of the emerging topics we cover in this conference, the many interesting optogenetics, super resolution imaging therapy, but also these luminescent materials can be developed used for thermometer. A lot of talks on thermometers. Maybe can be used for assistive technology. This is just my my proposals. I think with that, I'm going to stop my talk right here. Thank you.
Thank you, Xiaogang, for a wonderful presentation, really showing how our research can be translated to applications that are of real benefit for society. Yeah. Really wonderful.
Thank you.
Are there questions? Maybe while you think about the question, I can start with a question.
Sure.
A lot of your applications rely on defects. Mm-hmm. You showed your sodium lutetium fluoride, dopasturbium, you X-ray irradiated, then you have afterglow. Do you know the mechanism? I assume terbium traps the hole, but do you know what the electron trap is? And can you engineer it by maybe putting electron traps in to make it even more efficient?
Yeah, it's a great question. So I think for this position luminescence, we know very little about how they give the luminescence, the position luminescence. So most of I think suggestions is a defect, right? The traps, but we don't see that unless we have the technology, the tools can look at this individual defects. So the recent there's wonderful papers come out. Look at that's for single particle photocatalysis. The ultra-fast imaging technology, they actually look at the electron and hole recombination during the catalytic process. So I thought in our field, this luminescence either come from luminescent centers or traps. How we can visualize that, how we can trap that. So that's actually requires, I think, joint effort. Think about if you can look at that visualization, this process, that'd be tremendous.
Yeah, that's a real challenge in our field, understanding the defects.
I think it's possible. We have to combine the super resolution imaging, the ultra-fast imaging technology. So look at for example, individual particles with a defect. So it is possible, especially at that ultra-fast time scales. Maybe it's possible, yeah. But just people have to think about this problem, yeah.
Other questions?
No question? Good. So ready for the next.
So then let's thank Xiaogang for a wonderful and inspirational presentation.
Thank you.